Writing the symbols in a nuclear chemical equation. So, the key to answering these kind of questions is first of all looking at what kind of radioactive particle is involved and knowing how to write the symbol for that. So, common radioactive emissions is going to be alpha decay, which is a helium nucleus. So, you would just write that as 4, 2, and then helium. No good way to do this in Zoom. Okay. So remember that this number at the top is the mass number. So A is the mass number. So remember that's the number of protons plus neutrons. And then on the bottom, Z is your atomic number or the proton number. So that is only the number of protons. And then the element symbol is obviously whatever the element symbol is. So from this, we can see that a helium nucleus has two protons and two neutrons. Okay, so that would be an alpha particle. Just write alpha up here. A beta particle is an electron. Okay, now for subatomic particles, what you do for the atomic number is you just put the charge. So a beta particle is the same as an electron. So electron has no mass or negligible mass, and the charge is -1. So on the bottom, you put -1 for the electron, aka the beta particle, and then we would usually write electron like so. Other subatomic particles that are going to appear in nuclear equations is a positron, which is the antimatter partner of an electron. So a positron is a positively charged electron. So a positron still has zero mass, but will have a +1 charge instead of a -1 charge. And that would be a positron. Okay, so positron, we usually call it an E plus, I believe. And of course, other subatomic particles that might show up is a proton. And a proton has an atomic mass of 1 and a charge of +1. We learned this in Gen Chem 1, right? So usually the symbol for a proton is just going to be a P. And a neutron, of course, has the same mass as a proton, give or take, but zero charge. So we'd write the symbol for a neutron like so. 1, 0, and then an N. So if you know what kind of decay process, what kind of particles are being emitted or absorbed or whatever, then you're going to need to know how to write correctly the nuclide symbols for those particles. So in this case, we're talking about emission of an electron, which is beta decay. So we're going to need to know how to correctly write the form of electron in a nuclear chemical equation. So just like any mathematical equation, the numbers on each side have to match. So that means A, the mass number, has to match on both sides, and Z, the proton number, has to match on each side of the arrow sign. So look at them separately. Okay, so what I would do to answer this kind of question is that we know an electron is being emitted. So I will write the symbol for my electron like so on the product side because it's being emitted. And then I'm going to work out what on earth must be the other mystery nuclide that we have. So there's going to be an A, there's going to be a Z, and there's going to be then whatever the element is. Okay, so that's our mystery that we are trying to solve here. Okay, so first of all, A plus 0 must equal 99 for the sides to match. So that means that the mass number A is going to be unchanged. This is characteristic of beta decay, that the mass number is going to remain unchanged because an electron has zero mass. So Z minus 1 must equal 43. Therefore, Z must be 44, right? 44 minus 1 is going to equal 43. So this is very important for nuclear reactions, okay, because what's happening is the identity of the element changes if the proton number changes, right? That's like the fundamental definition of an element, that it is defined by the number of protons in the nucleus. So we have to find the symbol for what we call the daughter nuclide. So technetium-99 is the parent nuclide, and this new nuclide, which has Z of 44, still has a mass number of 99, is going to be our daughter. So you're going to need to get your periodic table and then look at what has Z of 44, and that is ruthenium. So an alchemical reaction, if you like, is what's happening. The only way you can transmute one element to another is in a nuclear reaction, right? So remember, if Z changes, then the actual element changes because there's a different number of protons in the nucleus. So we can see the net effect of beta decay is that a proton is added to the nucleus of whatever element is undergoing beta decay. So I guess I can show another one, probably if I can use the mouse real quick to see what other kinds of emissions we have. Dum 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 dum. So absorbing an electron. So if we're absorbing electron, that means the electron is going to be on the left-hand side of this particular nuclear reaction. And emitting a gamma ray. So gamma ray, if you see a gamma ray is just a photon, it's just electromagnetic radiation, it's energy. So there's zero mass and charge associated with a gamma ray. Okay, so we're absorbing an electron on the left-hand side. So I would have to put 0, -1, and E. Okay, so let's check and see if we're balanced. So -1 plus something must equal 38. I'm not going to have enough space to do this, am I? So my other nuclide must be -1 plus something equals 38. So it must be 39 on the bottom. I have to move this up here somewhere. So and then on the top, the mass number is going to be unchanged. So 0 plus something equals 88. So the number on top must be 88. So my proton number Z is changed. I have to get my periodic table and look at what has Z of 39. That is yttrium. And actually, we've been given a clue for that in the question. I'm not sure if I can fit this in here, but it should be on the left side of the equation, right? Because we're told that the yttrium-88 nuclide transforms into strontium-88. Okay, so we can see that that would be balanced. I'm just going to quickly see what other kinds of decay we might be asked about. Emitting an electron, absorbing an electron, emitting an alpha particle. There we go. Let's do that one as well, just to make sure we've done all the things. So if we are emitting an alpha particle, remember an alpha particle is a helium nucleus. There we go. So helium-4 nucleus. So 2 protons, 2 neutrons. So we want to make sure that this is balanced. So what do we have to have for our mass number? We have to have 4 plus x equals 180. Therefore, x must be 176. That's our mass number. And on the bottom, 2 plus x equals 74. So x is going to be 72. So to work out the element ID, we have to get our periodic table, look at what element has Z of 72, and that is hafnium. So you can check that we are balanced here. So there we go. There is our alpha particle decay. Okay, so 176 plus 4 equals 180. Check. 72 plus 2 gives 74. Check. And tungsten has changed into hafnium because if Z changes, that means the element itself has changed.